Learning objectives. By the end of this video, you will be able to explain what a correlation coefficient tells us about the relationship between two variables. Recognize that correlation does not indicate a cause and effect relationship between variables. Discuss our tendency to look for relationships between variables that do not really exist. Explain random sampling and assignment of participants into experimental and control groups. Discuss how experimenter or participant bias could affect the results of an experiment. Identify independent and dependent variables. Did you know that as sales in ice cream increase, so does the overall rate of crime? Is it possible that indulging in your favorite flavor of ice cream could send you on a crime spree? Or, after committing crime, do you think you might decide to treat yourself to a cone? There is no question that a relationship exists between ice cream and crime. But it would be pretty foolish to decide that one thing actually caused the other to occur. It is much more likely that both ice cream sales and crime rates are related to the temperature outside. When the temperature is warm, there are lots of people out of their houses, interacting with each other, getting annoyed with one another, and sometimes committing crimes. Also, when it is warm outside, we are more likely to seek a cool treat like ice cream. How do we determine if there is indeed a relationship between two things? And when there is a relationship, how can we discern whether it is attributable to coincidence or causation? Correlational research. Correlation means that there is a relationship between two or more variables, such as ice cream consumption and crime. But this relationship does not necessarily imply cause and effect. When two variables are correlated, it simply means that as one variable changes, so does the other. We can measure correlation by calculating a statistic known as a correlation coefficient. A correlation coefficient is a number from -1 to +1 that indicates the strength and direction of the relationship between variables. The correlation coefficient is usually represented by the letter R. The number portion of the correlation coefficient indicates the strength of the relationship. The closer the number is to 1, be it negative or positive, the more strongly related the variables are, and the more predictable changes in one variable will be as the other variable changes. The closer the number is to 0, the weaker the relationship, and the less predictable the relationships between the variables becomes. For instance, a correlation coefficient of 0.9 indicates a far stronger relationship than a correlation coefficient of 0.3. If the variables are not related to one another at all, the correlation coefficient is 0. The example earlier about ice cream and crime is an example of two variables that we might expect to have no relationship to each other. The sign, positive or negative, of the correlation coefficient indicates the direction of the relationship. A positive correlation means that the variables move in the same direction. Put another way, it means that as one variable increases, so does the other. And conversely, when one variable decreases, so does the other. A negative correlation means that the variables move in opposite directions. If two variables are negatively correlated, a decrease in one variable is associated with an increase in the other, and vice versa. The example of ice cream and crime rates is a positive correlation because both variables increase when temperatures are warmer. Other examples of positive correlations are the relationship between an individual's height and weight, or the relationship between a person's age and number of wrinkles. One might expect a negative correlation to exist between someone's tiredness during the day and the number of hours they slept the previous night. The amount of sleep decreases as the feelings of tiredness increase. In a real-world example of negative correlation, student researchers at the University of Minnesota found a weak negative correlation, R equals negative 0.29, between the average number of days per week that students got fewer than 5 hours of sleep and their GPA. Keep in mind that a negative correlation is not the same as no correlation. For example, we would probably find no correlation between hours of sleep and shoe size. As mentioned earlier, correlations have predictive value. Imagine that you are on the admissions committee of a major university. You are faced with a huge number of applications, but you are able to accommodate only a small percentage of the applicant pool. How might you decide who should be admitted? You might try to correlate your current students' college GPA with their scores on standardized tests like the SAT or ACT. By observing which correlations were strongest for your current students, you could use this information to predict relative success of those students who have applied for admission into the university. 3 scatter plots are shown. Scatter plot A is labeled positive correlation and shows scattered dots forming a rough line from the bottom left to the top right. The x-axis is labeled weight and the y-axis is labeled height. Scatter plot B is labeled negative correlation and shows scattered dots forming a rough line from the top left to the bottom right. The x-axis is labeled tiredness and the y-axis is labeled hours of sleep. Scatter plot C is labeled no correlation and shows scattered dots having no pattern. The x-axis is labeled shoe size and the y-axis is labeled hours of sleep. Scatter plots are a graphical view of the strength and direction of correlations. The stronger the correlation, the closer the data points are to a straight line. In these examples, we see that there is a positive correlation between weight and height, a negative correlation between tiredness and hours of sleep, and no correlation between shoe size and hours of sleep. Correlation does not indicate causation. Correlational research is useful because it allows us to discover the strength and direction of relationships that exist between two variables. However, correlation is limited because establishing the existence of a relationship tells us little about cause and effect. While variables are sometimes correlated because one does cause the other, it could also be that some other factor, a confounding variable, is actually causing the systematic movement in our variables of interest. In the ice cream crime rate example mentioned earlier, temperature is a confounding variable that could account for the relationship between the two variables. Even when we cannot point to clear confounding variables, we should not assume that a correlation between two variables implies that one variable causes changes in another. This can be frustrating when a cause and effect relationship seems clear and intuitive. Consider the research done by the American Cancer Society and how their research projects were some of the first demonstrations of the link between smoking and cancer. It seems reasonable to assume that smoking causes cancer. But if we were limited to correlational research, we would be overstepping our bounds by making this assumption. Unfortunately, people mistakenly make claims of causation as a function of correlations all the time. Such claims are especially common in advertisements and news stories. For example, recent research found that people who eat cereal on a regular basis achieve healthier weights than those who rarely eat cereal. Guess how the cereal companies report this finding? Does eating cereal really cause an individual to maintain a healthy weight? Or are there other possible explanations, such as someone at a healthy weight is more likely to regularly eat a healthy breakfast than someone who is obese or someone who avoids meals in an attempt to diet? While correlational research is invaluable in identifying relationships among variables, a major limitation is the inability to establish causality. Psychologists want to make statements about cause and effect, but the only way to do that is to conduct an experiment to answer a research question. The next section describes how scientific experiments incorporate methods that eliminate or control for alternative explanations, which allow researchers to explore how changes in one variable cause changes in another variable. Illusory correlations. The temptation to make erroneous cause and effect statements based on correlational research is not the only way we tend to misinterpret data. We also tend to make the mistake of illusory correlations, especially with unsystematic observations. Illusory correlations, or false correlations, occur when people believe that relationships exist between two things when no such relationship exists. One well-known illusory correlation is the supposed effect that the moon's phases have on human behavior. Many people passionately assert that human behavior is affected by the phase of the moon, and specifically that people act strangely when the moon is full. There is no denying that the moon exerts a powerful influence on our planet. The ebb and flow of the ocean's tides are tightly tied to the gravitational forces of the moon. Many people believe, therefore, that it is logical that we are affected by the moon as well. After all, our bodies are largely made up of water. A meta-analysis of nearly 40 studies consistently demonstrated, however, that the relationship between the moon and our behavior does not exist. While we may pay more attention to odd behavior during the full phase of the moon, the rates of odd behavior remain constant throughout the lunar cycle. Why are we so apt to believe in illusory correlations like this? Often we read or hear about them and simply accept the information as valid. Or we have a hunch about how something works and then look for evidence to support that hunch, ignoring evidence that would tell us our hunch is false. This is known as confirmation bias. Other times we find illusory correlations based on the information that comes most easily to mind, even if that information is severely limited. And while we may feel confident that we can use these relationships to better understand and predict the world around us, illusory correlations can have significant drawbacks. For example, research suggests that illusory correlations, in which certain behaviors are inaccurately attributed to certain groups, are involved in the formation of prejudicial attitudes that can ultimately lead to discriminatory behavior. Causality, conducting experiments and using the data. As we have learned, the only way to establish that there is a cause and effect relationship between two variables is to conduct a scientific experiment. Experiment has a different meaning in a scientific context than in everyday life. In everyday conversation, we often use it to describe trying something for the first time, such as experimenting with a new hairstyle or a new food. However, in the scientific context, an experiment has precise requirements for design and implementation. The experimental hypothesis. In order to conduct an experiment, a researcher must have a specific hypothesis to be tested. As you've learned, hypotheses can be formulated either through direct observation of the real world or after careful review of previous research. For example, if you think that children should not be allowed to watch violent programming on television because doing so would cause them to behave more violently, then you have basically formulated a hypothesis, namely that watching violent television programs causes children to behave more violently. How might you have arrived at this particular hypothesis? You may have younger relatives who watch cartoons featuring characters using martial arts to save the world from evil doers with an impressive array of punching, kicking, and defensive postures. You notice that After watching these programs for a while, your young relatives mimic the fighting behavior of the characters portrayed in the cartoon. These sorts of personal observations are what often lead us to formulate a specific hypothesis, but we cannot use limited personal observations and anecdotal evidence to rigorously test our hypothesis. Instead, to find out if real-world data supports our hypothesis, we have to conduct an experiment. Designing an experiment. The most basic experimental design involves two groups, the experimental group and the control group. The two groups are designed to be the same, except for one difference: experimental manipulation. The experimental group gets the experimental manipulation, that is, the treatment or variable being tested, in this case, violent TV images, and the control group does not. Since experimental manipulation is the only difference between the experimental and control groups, we can be sure that any differences between the two are due to experimental manipulation rather than chance. In our example of how violent television program might affect violent behavior in children, we have the experimental group view violent television program for a specified time and then measure their violent behavior. We measure the violent behavior in our control group after they watch non-violent television program for the same amount of time. It is important for the control group to be treated similarly to the experimental group, with the exception that the control group does not receive the experimental manipulation. Therefore, we have the control group watch non-violent television program for the same amount of time as the experimental group. We also need to precisely define or operationalize what is considered violent and non-violent. An operational definition is a description of how we will measure our variables, and it is important in allowing others to understand exactly how and what a researcher measures in a particular experiment. In operationalizing violent behavior, we might choose to count only physical acts, like kicking or punching, as instances of this behavior. Or we also may choose to include angry verbal exchanges. Whatever we determine, it is important that we operationalize violent behavior in such a way that anyone who hears about our study for the first time knows exactly what we mean by violence. This aids people's ability to interpret our data, as well as their capacity to repeat our experiment should they choose to do so. Once we have operationalized what is considered violent television programming and what is considered violent behavior for our experiment participants, we need to establish how we will run our experiment. In this case, we might have participants watch a 30-minute television program, either violent or non-violent, depending on their group membership, before sending them out to a playground for an hour, where their behavior is observed and the number and type of violent acts is recorded. Ideally, the people who observe and record the children's behaviors are unaware of who was assigned to the experimental or control group, in order to control for experimenter bias. Experimenter bias refers to the possibility that a researcher's expectations might skew the results of the study. Remember, conducting an experiment requires a lot of planning, and the people involved in the research project have a vested interest in supporting their hypotheses. If the observers knew which child was in which group, it might influence how much attention they paid to each child's behavior, as well as how they interpreted that behavior. By being blind to which child is in which group, we protect against those biases. This situation is a single blind study, meaning that one of the group's participants are unaware as to which group they are in, experiment or control group, while the researcher who developed the experiment knows which participants are in each group. In a double-blind study, both the researchers and the participants are blind to group assignments. Why would a researcher want to run a study where no one knows who's in which group? Because by doing so, we can control for both experimenter and participant expectations. If you're familiar with the phrase placebo effect, you already have some idea as to why this is an important consideration. The placebo effect occurs when people's expectations or beliefs influence or determine their experience in a given situation. In other words, simply expecting something to happen can actually make it happen. The placebo effect is commonly described in terms of testing the effectiveness of a new medication. Imagine that you work in a pharmaceutical company and you think you have a new drug that is effective in treating depression. To demonstrate that your medication is effective, you run an experiment with two groups. The experimental group receives the medication and the control group does not. But you don't want participants to know whether they receive the drugs or not. Why is that? Imagine that you are a participant in this study and you have just taken a pill that you think will improve your mood. Because you expect the pill to have an effect, you might feel better simply because you took the pill and not because of any drug actually contained in the pill. This is the placebo effect. To make sure that any effects on mood are due to the drug and not due to expectations, the control group receives a placebo, in this case, a sugar pill. Now, everyone gets a pill, and once again, neither the researcher nor the experimental participants know who got the drug and who got the sugar pill. Any differences in mood between the experimental and control groups can now be attributed to the drug itself rather than to experimenter bias or participant expectations. Independent and dependent variables. In a research experiment, we strive to study whether changes in one thing causes changes in another. To achieve this, we must pay attention to two important variables, or things that can be changed, in any experimental study: the independent variable and the dependent variable. An independent variable is manipulated or controlled by the experimenter. In a well-designed experimental study, the independent variable is the only important difference between the experimental and control groups. In our example of how violent television programs affect children's display of violent behavior, the independent variable is the type of program, violent or nonviolent, viewed by participants in the study. A dependent variable is what the researcher measures to see how much effect the independent variable had. In our example, the dependent variable is the number of violent acts displayed by the experimental participants. We expect that the dependent variable will change as a function of the independent variable. In other words, the dependent variable depends on the independent variable. A good way to think about the relationship between the independent and dependent variables is with this question: what effect does the independent variable have on the dependent variable? Returning to our example, what effect does watching a half hour of violent television programming or non-violent television programming have on the number of incidents of physical aggression displayed on the playground? Selecting and assigning experimental participants. Now that our study is designed, we need to obtain a sample of individuals to include in our experiment. Our study involves human participants, so we need to determine who to include. Participants are the subjects of psychological research, and as the name implies, individuals who are involved in psychological research actively participate in the process. Often, psychological research projects rely on college students to serve as participants. In fact, the vast majority of research in psychology subfields has historically involved students as research participants. But are college students truly representative of the general population? College students tend to be younger, more educated, more liberal, and less diverse than the general population. Although using students as test subjects is an acceptable practice, relying on such a limited pool of research participants can be problematic because it is difficult to generalize findings to the larger population. Our hypothetical experiment involves children, and we must first generate a sample of child participants. Samples are used because populations are usually too large to reasonably involve every member in our particular experiment. If possible, we should use a random sample. There are other types of samples, but for our basic purposes, we will focus on random samples. A random sample is a subset of a larger population in which every member of the population has an equal chance of being selected. Random samples are preferred because if the sample is large enough, we can be reasonably sure that the participating individuals are representative of the larger population. This means that the percentages of characteristics in the sample, sex, ethnicity, socioeconomic level, and any other characteristics that might affect the results are close to the percentages in the larger population. In our example, let's say we decide our population of interest is 4th graders, but all 4th graders is a very large population, so we need to be more specific. Instead, we might say our population of interest is all 4th graders in a particular city. We should include students from various income brackets, family situations, races, ethnicities, religions, and geographic areas of town. With this more manageable population, we can work with local schools in selecting a random sample of around 200 4th graders who we want to participate in our experiment. Now that we have a sample, the next step of the experimental process is to split the participants into experimental and control groups through a random assignment. With random assignment, all participants have an equal chance of being assigned to either group. There is statistical software that will randomly assign each of the 4th graders in the sample to either the experimental or the control group. Random assignment is critical for sound experimental design. With sufficiently large samples, random assignment makes it unlikely that there are systematic differences between the groups. So, for instance, it would be very unlikely that we would get one group composed entirely of males, a given ethnic identity, or a given religious ideology. This is important because if the groups were systematically different before the experiment began, we would not know the origin of any differences we find between the groups. Were the differences pre-existing, or were they caused by manipulation of the independent variable? Random assignment allows us to assure that any differences observed between experimental and control groups result from the manipulation of the independent variable. Issues to consider. While experiments allow scientists to make cause and effect claims, they are not without problems. True experiments require the experimenter to manipulate an independent variable, and that can complicate many questions that psychologists might want to address. For instance, imagine that you want to know what effect sex, the independent variable, has on spatial memory, the dependent variable. Although you can certainly look for differences between males and females on a task that taps into spatial memory, you cannot directly control a person's sex. We categorize this type of research approach as quasi-experimental and recognize that we cannot make cause and effect claims in these circumstances. Experimenters are also limited by ethical constraints. For instance, you would not be able to conduct an experiment designed to determine if experiencing abuse as a child leads to lower levels of self-esteem among adults. To conduct such an experiment, you would need to randomly assign some experimental participants to a group that receives abuse, and that experiment would be unethical. Interpreting experimental findings. Once data is collected from both the experimental and the control groups, a statistical analysis is conducted to find out if there are meaningful differences between the two groups. A statistical analysis determines how likely any difference found is due to chance, and thus not meaningful. In psychology, group differences are considered meaningful or significant if the odds that these differences occurred by chance alone are 5% or less. Stated another way, if we repeated this experiment 100 times, we would expect to find the same results at least 95 times out of 100. The greatest strength of experiments is the ability to assert that any significant differences in the findings are caused by the independent variable. This occurs because random selection, random assignment, and a design that limits the effects of both experimenter bias and participant expectancy should create groups that are similar in composition and treatment. Therefore, any difference between the groups is attributable to the independent variable, and now we can finally make a causal statement. If we find that watching a violent television program results in more violent behavior than watching a non-violent program, we can safely say that watching violent television programs causes an increase in the display of violent behavior.